In this video, I will concentrate on the analysis of energy levels of a rigid diatomic rotor, and at the end we will end up with the position of the spectral lines that will be obtained from microwave spectroscopy. So firstly, to have the energy levels, we have to solve the Schrodinger equation for the rigid diatomic molecule. That is a very hectic work, and after the solution is done, we have the energy levels for a rigid diatomic molecule to be Ej, J means quantum number. For the rotation, it will be h square upon 8 pi square I, J into J plus 1. This is the energy expression. This h is the Planck's constant, I is the moment of inertia that I have determined in the previous video. It is mu r square, where r is the bond length and mu is the reduced mass of the diatomic rotor, and J is the rotational quantum number whose allowed values are 0, 1, 2, 3 and so on. Now these values are no means arbitrary. This appears from the solution of the Schrodinger equation. This reveals that the energy levels are discrete, and it is discrete because we are dealing with a microscopic particle, and here the quantization appears because of the restriction of the quantum mechanical nature. Now it is comfortable to get the spectrum in terms of wave number. So we will switch from joule to centimeter inverse or arg to centimeter inverse. However, the idea or the objective will remain the same, since both of them will represent the same thing. So what is the relation? Let us represent the energy in terms of wave number, and let us use the symbol epsilon instead of E. So epsilon will be related to E by this equation. Dividing energy in joule or arc by Hc, it will give us the energy in terms of wave number, that is centimeter inverse or meter inverse. Now what it will give us? H square upon 8 pi square I into Hc, it will be J into J plus 1. So it will be H upon 8 pi square Ic into J plus 1. This H is constant, I is constant for a particular system, C is the velocity of light, it is constant. So we replace this term by B. So this is the expression of energy of a rigid diatomic rotor in terms of wave number, where this B is the rotational constant and J is the rotational quantum number. Now since this J is quantum number, this will be dimensionless. So the dimension of B must be centimeter inverse, since here we have wave number. So let us check this. B equals to H upon 8 pi square Ic. So H is arg second. Now what is arg? It is dyne centimeter. So it will be dyne centimeter second. And for I it will be reduced mass, and reduced mass is defined as m1 m2 upon m1 plus m2. So gram into gram by gram plus gram. So it will be gram. We write here G, pi is dimensionless, 8 is constant, and here we have r square, so it will be centimeter square, and C is centimeter per second. Now this centimeter will cancel out, and we have dyne. So dyne will be gram centimeter per second square. Dyne is that force with which when acts on a mass of 1 gram produces in it an acceleration of 1 centimeter per second square, and arg is the work that is associated upon displacement of 1 centimeter in the direction of the force, and the force applied is 1 dyne. So it is gram centimeter per second square into this second, and this second inverse will come up and it will be second square, and here we have gram centimeter square. These two will cancel each other, gram will cancel, centimeter and this power will cancel. So this centimeter will go up and we will have the dimension of B to be centimeter inverse as expected. So this is correct. Now, what are the energy levels? So first, let us draw the axis that will represent energy in terms of wave number. For J equal to 0, what will be the energy? It will be 0 into these terms, so energy will be 0. So this is the energy of the ground state. What it means is that the molecule will not rotate, since the rotational energy will be 0. Now, the first excited state, it will appear with the least rotational energy, least angular momentum, and it will be for J equal to 1. So it will be 1 into 1 plus 1, 2B. Epsilon 1, the energy for the first excited state will be 2B for J equal to 1. Now for J equal to 2, it will be 2 into 3, so 6B. In a similar way, for epsilon 3, it will be 3 into 4, so 12B for J equal to 3, and it will be 20B for J equal to 4. So the energy gap is increasing. The gap between the ground state and the first excited state is 2B. Between the first and the second excited state is 6B minus 2B, it is 4B. Between second and third excited state, it is 12B minus 6B, so it is 6B, and here it is 8B. So the gap is increasing gradually with increase in the rotational quantum number. In principle, we can calculate epsilon j for increasing values of j without any restriction. There is no upper limit, no restriction from the Schrodinger equation. Even for very, very high value of j, there will be the corresponding energy. But what happens in case of real molecules is that when it rotates, centrifugal force acts on the atoms. and for very high value of J, the centrifugal force will be very high, and a point may appear where the centrifugal force is greater than the bond strength. Then what will happen? The atoms will get apart from each other and the diatomic molecule will break apart. So in reality there is restriction. So why such discrepancy between theory and experiment? This is because the molecule is not at all rigid. It is actually non-rigid, but we are using the equation for rigid rotor. Hence the message of disruption of atoms with increase in J is not coming from the theory. But such state of disruption will not be achieved or cannot be achieved at ordinary temperature. Hence, we can use the energy expression of rigid rotor to a very good approximation. Now, the study of energy difference is very important, since our main target is to find the position of the spectral lines. So, let us calculate del epsilon. Now, del epsilon means energy of the excited state or final state minus energy of the initial state. Now, what value we should put here? That will be guided by selection rule, and I have already discussed what is that selection rule, what selection rule means. Now for this rigid rotor case, del J will be plus minus 1. In the upcoming video where I will discuss the intensity of the rotational spectral lines, I will again discuss this issue. So del J equals to plus minus 1 only means that we can write here J, it is the initial, and here it will be J plus 1. So we put the values. We can remember that epsilon J is B into J plus 1. So putting J plus 1 in place of J will be this, and here it will be J plus 1 plus 1. It is actually J into J plus 1, but we are putting J plus 1 instead of J. So the equation will look like this, the first term, and the second term, that will be B into J plus 1, since here it is J only. Now we will take B into J plus 1 common. B into J plus 1 common. So it will be J plus 2 minus J. J will cancel out, or del epsilon will be 2B into J plus 1. Del epsilon will be 2B into J plus 1. Now we have already find out that 2B, 4B, 6B, 8B are the difference in energy in the successive energy levels. So we will check whether this formula is right or not. In the first case, del epsilon 0 to 1, that is for the transition from ground to the first excited state. We will put here 0, since this is J and this is the initial one. So this J will represent the initial state. So we will put here 0. It will be 2B into 0 plus 1. Hence it will be 2B. So the first energy gap between the first excited state and the ground state will be 2B. It is matching. Between the first and the second excited state, it will be 2B into 1 plus 1. So it will be 4B. It is matching. In a similar way, from 2 to 3, it will be 2 plus 1, 3 into 2. So it will be 6B. 3 to 4, will be 8b and so on. Now it's time to have the peak. So this is this y-axis will represent the intensity. I will discuss intensity in the upcoming videos. At present, let us make intensity of all the spectral lines equal. We will consider only the position in this video. Then we will improve the spectra one by one. Now here we will put new bar and here it is intensity. So what will be the position of the first line? We will scan the microwave region, and if we start from 0, then after reaching 2b from 0 we will get the first line, since this is the energy gap between 0 and 1. So when the energy gap 2b is supplied by the photon, the energy required for the transition 0 to 1 is supplied by the incident radiation, then the first transition will occur and we will get a line at the position 2b from 0. So here we will get a line. This will correspond the transition from ground state to the first excited state. And then the second is from 1 to 2. So it will require an energy 4b. So we are increasing energy from 0. So here it is 2b. Now when we get 4b from the beginning, we will get another line. It will correspond 1 to 2. Then at 6b. So it is 0 to 2b, then 3b, then 4b, then 5b, then 6b. At 6b, which will correspond 2 to 3, we will get another line. In this way, 3 to 4 and so on. Now what we get is that all the lines are equispaced. All the rotational spectral lines are equispaced. That is the graph that we are obtaining from the spectrophotometer. In that graph, the lines will be equidistant from each other, and those lines will be separated by 2b. Now, I will give you some homework, and in the next video or upcoming video, I will discuss regarding the intensity and some further details of this spectra. So what will be the homework? For a rigid diatomic molecule, I have already discussed that IA will be 0 and IB equals to IC. Now in the equation, B equals to H upon 8 pi square IC. What this I will represent? This will represent either IB or IC. Then the question is it possible to have rotational spectral lines corresponding to the moment of inertia around the bond axis? For rotation around the bond axis, is it possible to get spectral lines? The spectral lines we have obtained just now will correspond to IB or IC. Question is it possible to have spectral lines for IA, that is rotation around the bond axis? This is the first question. And the second question is, even for IB and IC, how the first line appears? First line means this one for 0 to 1. Why I am putting such question? Since when it is in the 0 state, it will have energy 0. B into J plus 1. So its energy will be 0. Energy 0 means there will be no rotation. No rotation means no oscillation in dipole moment. Then it will not interact with the microwave radiation. So how the first line appears? That is a vital question. How the first line appears at position 2B from the start, from the beginning. How? Please answer these two questions.